Hi everyone, welcome. Today we are very happy to have Fedor Popov from Simon Center, who's going to tell us about entropic order.
It's a great pleasure for me to come to Ishihag again. Last time I was 4 years ago, and we talked about some unusual behavior in quantum field theory. But this unusual behavior was happening in non-unitary models. Today I will talk about some non-interesting behavior in various models, quantum field theory and lattice models, but now they will happen in a natural number of dimensions. They will be unitary and they will be lattice models, lattice models. So today I will talk about my recent research. It is devoted to the question, if you put in the break form, whether it's possible to have high temperature superconductivity, or if you want to put in the most modest way, whether it's possible to have spontaneous symmetry breaking at arbitrarily high temperatures. And we found a lot of interesting examples where it can happen. For instance, in this first work that was published this first work, I will put it out of order. In this first work that was almost published a year ago, and Zohar Komargovsky found an interesting QFT model where exhibits spontaneous symmetry breaking at all temperatures, some CFT. After that, together with Andrew Lucas, who is professor at the University of Boulder, and two of his students, we made some observation about that model and some observation from real life that allows us to come up with some paradigms that explain this strange behavior in our original model. And extending this paradigm to lattice models, we managed to construct some interesting lattice models that exhibit the symmetry breaking at very arbitrarily high temperatures, up to infinity. And these paradigms that we decided to call as entropic order, as opposed to the energetic order that we all know from usual class of statistical mechanics. And recently, together now with Tim Suleiman-Pasic, who is professor at University of Durham, we constructed some other minimal models of entropic orders that finally could be realized in real life. So the main goal of my talk is to present what this entropic order is and explain how it works in these various models. I will try to be a little bit more basic, but still, if you have any questions, feel free to stop me and I will be very happy to answer on all of them. So the plan of my talk is the following. First, I will briefly review foundations of phase transition and why we believe that to have spontaneous symmetry breaking at arbitrarily high temperatures, it sounds bizarre. After that, I will give you some interesting counterexamples from the real world, so-called Rochelle salt and Pomeranchuk effect, that defies this original idea that symmetry breaking can occur on that low temperatures. And after that, I will try to refine a little bit this original argument that we all know from the class of statistical mechanics by using some mass intuition. And I will tell you about this Dobrushkin uniqueness, actually theorem, not criterion, you can call it theorem, criterion, that actually will point out, tell us that in the wide classes of lattice models, we must not have spontaneous symmetry breaking at high temperatures. But this theorem actually will point out which type of models we must look at, where this type of behavior could happen. And after that, with the use of this theorem, I will show you that there exists lattice example and QFT examples, where you have this interesting behavior. And maybe at the end, I will briefly tell you how to realize them on the experiment. Okay, so let me start with a little introduction. So since the ancient times, people observed that matter consists of some invisible particles called atoms, and they interact in some particular way, like here. And this interaction does not depend on external conditions, but somehow by varying these external conditions, we get completely different states. For instance, if you study a bunch of H2O molecules at high temperatures, they become liquid. You can change the form, but as soon as you cool it down, it becomes solid and completely changes its behavior. For instance, I can distinguish with the naked eye between these two phases, between liquid, water, and solid. And people got amused by this phenomenon since the ancient times. They tried to understand it, why it happens, why does it happen in particular conditions, and so on. But the first question they had to address is how do you distinguish these two phases? And depending on the zeitgeist of the time, they got different questions, different answers. The first answer was just to do some subjective rating, like this one. Or after people do scientific revolutions, they try to do some sort of decision trees. But this answer will not satisfy because they were not mathematically rigorous until 1890s, when Pierre Curie discovered spontaneous magnetization. And from the time for scientific community, that observation was very peculiar. So what did Pierre Curie did? He took just metal and studied what happened to it once you sufficiently cool it down. And he observed once you sufficiently cool it down below some critical temperature, I just put here one, he observes that it becomes spontaneously magnetized. So you can imagine that metal consists of a lot of random spins, but for high enough temperatures, these random spins randomly located, and the total magnetization averages to zero. But below some critical temperature, somehow these spins decided not to randomly orient with each other. They decided to be directed in one direction and create some sort of magnetic field. And finally, you can, for instance, attach it to your refrigerator. But this phenomenon is very strange because of the fundamental laws of physics describing the interaction of the spins actually respects the rotational symmetry. And you see that this state actually breaks this rotational symmetry to a subgroup that corresponds to a group that rotates around this direction. And Pierre Curie didn't manage to accept this on experiment, and he thought this was some sort of external factor that he didn't manage to get out. And he thought that in through setup that doesn't have some external influence, he would always get this setup. But nonetheless, additionally with that interesting phenomenon, he observes that this transition from this state to this state, according to the old definitions of phase transition, should be classified as a phase transition. Based on this observation, some other observation, Lev Landau, a Soviet physicist, proposed the following classification of phase transitions by stating that phase is just a symmetry breaking pattern of a theory. So what it means? It means that you take some theory. For instance, it could be just molecules interacting with each other, or some sort of 5 to the 4th model. I forgot to write here the kinetic term for this field M. You study the symmetries of that theory, and you see that first of all, the symmetry of the theory include all shifts and rotations, usually Euclidean group, but also could include some internal symmetry. For instance, in the case of Ising model, it could be the two symmetries, in a sense M to minus M. And after that, you study how the state of your theory depends on various conditions. And if the state of the theory respects only some part of the original symmetry, you say that symmetry is a symmetry broken phase, and this pattern is exactly the group that it respects. And after that, you say that your theory exists in the same phase if the symmetry breaking pattern is the same. For instance, in the case of water, you have solid phase that breaks shift symmetry. In the liquid phase, this phase is restricted. And after that, a lot of phase transitions that people knew for that time fell nicely into this classification. And from now on, people they don't see some symmetries that got broken from the phase transition. People still try to generalize this notion of a symmetry and states that now this symmetry is got broken. Okay, so now we understand how phases are connected to spontaneous symmetry breaking. And to answer the question, like if I want to have, for instance, solid at very high temperatures, or say superconductor at very high temperatures, I just need to understand how to make spontaneous symmetry breaking persistent to high temperatures. Yes, but as we know from the classes on statistical mechanics, usually we assume that at low temperatures symmetry is maximally broken, and at high temperatures the symmetry must be restored. And the argument is going as follows. You start with the assumption that you have some theory that is odd under that has no trivial action of C2 symmetry. It means then that I have some some operator, some observable M that is under C2 symmetry. And after that, you make an assumption that the energy profile of the theory depends in the following way. So it creates the following double wave potential with minimum as minus A, and the maximum at 0. And after that, you just study the one-point correlation function of this quantity at different temperatures. Using usual laws of thermodynamics, this amount just to computation of this integral. And you see that at low temperatures, it means that I should study the theory around its vacuum state, around here or here. And if I do that, I will put my system initially around one of these vacuum states, say here. And after that, I will wait long enough and see how my system will behave. Once I do it, I will see that most of the time my system will behave here. It will never go to the state because of thermal fluctuations are small. Of course, at some time, maybe in 1,000 years, at 10,000 years, the fluctuations will be strong enough, and finally my system will observe this universe. But for the time of this observation, most of the time, my system will stay around one of the vacuum states. For instance, here. And whenever I will measure this M, I will declare that it's potentially broken by symmetry because of M now is not equal to 0, it's equal to some particular value A. Okay. As soon as I start to heat it up my system, I will notice that fluctuation becomes so strong, and finally my system will try to propagate here and observe this thing. After speaking what is happening, when I increase temperature T, that factor gets completely annihilated, it just vanishes here. And finally, I just average this O of whole phase space of my theory. And of course, when I average this operator over all my phase space, I must get 0 here. Here. And from that, we claim that at high temperatures, we must have restoration of the symmetry. At small temperatures, we have breaking of the symmetry. And after speaking, we just say that at T goes to 0, we maximize energy, and energy usually associated with order. And at infinite temperature, we maximize entropy. And hence, we try to make average of all possible symmetry broken universes, roughly speaking. So it seems nicely fit into all our observations, and maybe it's correct, but actually nature provided us with quite interesting two counterexamples to this interesting phenomenon. The first one phenomenon is quite simple, and it's not something supernatural. It's so-called Roche salt. It's not something complicated. You can go to Amazon right now and order it. It's some sort of medicine that people use. And it has an interesting property that is, as in the case of the Pierre Curie experiments, it actually gets magnetized at some range of temperatures. But this range of temperature is from minus 20 Celsius up to 35 Celsius here. So we see that our initial logic that at low temperatures we should maximally break our symmetry, and at high temperatures we must restore it, is broken here. The order is reserved, and at high temperatures we have the symmetry broken phase. But the miracle does not happen, and still at very high temperatures we have restoration of symmetry. At around 35 Celsius, this magnetization fails. There is a nice theory that explains it. I will come back to it in a moment. The other effect is much more interesting. It's so-called Pomeranchuk effect. And for that, you cannot order this material from Amazon. You need to go to some special lab. You just take liquid helium-3 and study it at very high pressure, at 10 to the 5 atmospheres. And after that, you study the phase diagram of that system, and you will see that at low temperatures, it is in a liquid phase, and high temperature, it is a solid phase. And the interesting thing about that, because of at first glance, it looks like it's a usual phase diagram for, say, H2O, for water. The phase transition here has actually negative latent heat. So it means that if I take the ice cube of liquid helium-3 and put into a hot beverage, instead of cooling down this beverage, it will heat it up. But actually physicists use it not in this way, they use it in a different way. They just put this liquid helium-3 next to the sample that you want to study at very low temperatures, like this one. And once you cool it down, it also will absorb energy from surrounding sample and allows you to reach this very low temperatures, around 1 millikelvin. But now Cry starts using much more sophisticated techniques than this one. So it's quite an interesting phenomenon. And the explanation was that was given by Pomeranchuk, who said that the entropy of the liquid state is actually lower than the entropy of the solid state. This picture I took actually from this paper by Pomeranchuk. And here he drew a line for the entropy of the liquid state, and here he drew a line for the entropy of the solid state. And he said that this entropy in the ordered state coming from the additional vibrational degrees of freedom that lives on the lattice once this liquid helium-3 gets crystallized. And that's why the entropy of the solid phase becomes higher than the entropy of the liquid state. And he made some estimations and shows that that indeed the latent heat that he gets out of the simple model coincides with the latent heat that you get from the experiment. And now if you read the phenomenological explanation for the Rochelle salt, you will find out that actually the same type of mechanism is applicable here. When it's get to the ordered state, it opens some additional degrees of freedom that allows you to increase this entropy here. So we see that here we have another example to the previous argument, where the associated order with energy here, we must associate order with entropy. So maybe that could be some general mechanism that will allow us to construct different models, where we would have order coming from the entropy rather than from the energy. Interesting fact about Rochelle's salt that Steven Weinberg got fascinated by this phenomenon that he tried to construct the same type of theory that quantum field theory that would also exhibit this interesting property that at low temperatures it respects symmetry, but at high temperature it breaks symmetry. Okay. So let us try to understand where our previous argument was incorrect. And to do that, I must explain to you rigorously what is a spontaneous symmetry breaking from the point of view of from the mathematical point of view, to define it much more rigorously. And to do that, I will try to explain to you, remind you why spontaneous symmetry breaking occurs in classical mechanical system, doesn't occur in quantum mechanics, and again occurs in quantum field theory. So in classical mechanics, we again will try to study what is happening with the ground state of a particle living in the following potential. So it's the same double potential that I took from the previous two slides. So if I want to study classical particle at zero temperature, it means that I need to put it in some equilibrium state. There exist three equilibrium states, this one, and this one. And these equilibrium states could be split into groups. The first group is this two. They have minimal energy, but they break explicitly symmetry. The last group is this one that respects symmetry but has maximal symmetry. It respects the C2 symmetry. And assumes that I want to put my classical system at equilibrium and respect the symmetry. Then I'm forced to put my particle here. I will spend a lot of mental energy because of any small deviation from this point will immediately force my particle to move either this vacuum or this vacuum. But once I do it, I will find out this system becomes very unstable. Any small perturbation or tremor will immediately push my system into one of these vacuum states here. Hence, in classical mechanics, I have spontaneous symmetry breaking because of not because of this system has a maximal energy, this one's minimum energy, because of that state is unstable to small perturbations. Now, if I study classical quantum mechanical system here, I will note that when my system goes here, there is non-zero probability, transition probability from this vacuum state to this vacuum state. And hence, to get the correct vacuum state here, I must take into account this process of tunneling from this vacuum state to this vacuum state. And then I will get immediately that the ground state of the state is symmetric with respect to this symmetry C2. Roughly speaking, we just establishing of this so-called Perron-Proteus theory that states that the quantum mechanical system must be unique. And hence, roughly speaking, it happens because of we have non-zero transition probability from vacuum state to another state. And hence, to get spontaneous symmetry breaking, I need somehow to suppress my transition probabilities from vacuum state to another vacuum state. I can do it in three ways. The first way is quite simple. I just take Planck constant and send it to zero. It effectively kills my transition probability from this vacuum state to this vacuum state, but it reduces me back to classical mechanics. The other thing that I can do is much more interesting, is to keep Planck constant finite, but send the interaction strength to infinity here. So I will drag this potential of speaking to minus infinities here. Or I will drag this sum to infinity. Yeah? Then I will see that my Hilbert space gets split into two halves. The first universe will live into this part. The second universe will live into this part. In each of these universes, I have approximately the same eigenspectrum. So for each eigenvalue here, I have exactly the same eigenvalue here. All the functions get localized, I said, here and here. And any local operator in my theory, A, it could be like a product of X and P, has zero overlap between these two states from these two different universes. So from that, I can say that here I have spontaneous symmetry breaking. And let me contrast quickly with the situation when I have just degenerate spectrum in quantum mechanics. For instance, I would consider spin one-half particle in zero magnetic field. I would also have that I have also two degenerate ground state, say plus spin and minus spin, but the algebra of local operator would allow me mixing between these two states here. Okay. But to replicate, but this again a little bit sick limit because of I'm taking this strange limit of lambda goes to plus infinity. And the last choice what is left is just to consider the infinite number of copies of the same potential. Then, by the same law of probabilities, I would have again that my Hilbert space gets split into two parts. The one that completely lives on this side here, and the other part that lives completely on this side. And again, I will see the same picture that my Hilbert space get double degenerate, and the algebra of local operators does not allow me mixing between these two universes. And from that, I will declare that it is spontaneous symmetry breaking. But you might say that since it's quantum mechanics, you can construct a state that is a linear combination between these two states. This one living on this universe, and this one living on this universe. So I can construct the following combinations. Say rho is equal to 1/2 rho plus 1/2 rho minus. But as in the case of the classical particle and its symmetric state, I will notice that this combination is highly unstable to small perturbations. For instance, if you follow Bogolyubov, who suggested that let us study stability of this combination under small perturbation, like you add some symmetry breaking term explicit to a Hamiltonian. If it's extremely sensitive to this small perturbation, epsilon b, you will see that you are either going from the symmetric state, will go to say either rho plus or rho minus. Or if you follow Bruyel, you can say break. You can add this perturbation by setting up some boundary conditions at infinity. By setting that at infinity, all of them go to A. So it means that from that we have a nice definition of spontaneous symmetry breaking. So we just ask whether we have two different superselection sectors in my system. And if you are given some symmetric state, you study whether it's stable under small perturbation. So to check, to prove that your system does not have spontaneous symmetry breaking, you either prove that this rho is unique, or if you want to prove it, you just study whether it's small under small perturbations. Okay. So now from that, we can go a little bit to a very interesting part. The next slide will be very interesting. So from that, we can prove the following two theorems. They're all by Robert Dobrushin, another Russian mathematician. He's probabilist, a student of Andrei Kolmogorov, who proves the following interesting theorem. They all have the same assumption. So assume that you have some model, some lattice system. You make the first assumption that you can split your Hilbert space into two parts sometimes. So if you have some model, some lattice, and you cut out some sublattice out of it, you say that your Hilbert space is factorized into Hilbert space of inside and Hilbert space of outside of your system. So for instance, gauge theory wouldn't satisfy this condition. The other condition is that once you cut out this finite sublattice, the system has a maximally mixed identity state. Roughly speaking, it means that the dimension of your Hilbert space is finite. And last assumption is that your interaction is finite. So you don't allow interaction spins with that are very far away separated. You allow interaction if only they are close to each other. Then Dobrushin managed to prove in these two cases the following two theorems. The first theorem is very abstract but very useful because of its abstract generate to all models. He managed to prove that for these models, for high enough temperatures, you must have a unique state at this temperature. How he proved it? he did it the following way. So he says that if you have this density matrix rho, it must satisfy the following condition, like this one. It's called sometimes TLR condition, and actually you might have heard about this condition from Min-J Stock, who actively uses this condition to bootstrap Ising model. But here we will try to do something opposite. Here we will study this mapping T, this DLR condition, and we'll just observe that our density matrix rho is the fixed point of this map T. And hence, if I prove that this fixed point is unique, I will prove immediately this rho is unique, and hence my system cannot have spontaneous symmetry breaking. And by studying explicitly how this T acts in the space of all possible density matrices, Dobrushin, with the use of this assumption that there exist maximally mixed identity states, managed to prove that there exists some particular temperature T, such that this map T is contracting. And from that, we must immediately get that this rho must be unique. Because if rho was not unique, I will subtract from one another and get that rho 1 minus rho 2 is equal to rho 1 minus 2 rho 2. But since T is contracting, the distance between these two states must get shrinked. So I cannot say that must declare that this equation must have only one solution.
What does this T do?
T?
Yeah, what is like?
Roughly speaking, it just states that each spin lives in the mean field created by the other spins. So just the law of total probabilities in some sense. The probability of find sigma field is equal to probability of find sigma given something outside, multiplying by probability of being something outside. So this factor just tells you that what probability to find spin sigma given that you have this sorry. So it just tells you that it exists in the field of the other fields created here. Just some rewriting of the partition function by analytical states, but you after that read this as some mapping into the space. Okay. The other theorem that Dobrushin proves that there exists high temperature expansion here was that he took finite lattice lambda, put some other condition on it, and since we have locally maximally mixed state, such expansion must exist here. And after that, carefully take into account how this expansion behaves if lambda goes to infinity. One can prove that this expansion exists for infinite lattice and it has finite radius of convergence for T bigger than T star. And after that, you can immediately prove that for temperatures bigger than T star, we must have symmetry restorations. If you have some odd operator phi, just sandwiching with respect to or expanding this e to the minus ht, you get infinite sum, and this infinite sum has zeros at each term, and after that you will get zero. So from that it seems that we cannot have persistent symmetry breaking at high temperatures because of these two theorems, but they have very weak assumptions, namely that assumptions of existence of maximally mixed identity state locally. And this assumption is quite strong because, for instance, for a lot of lattice models, this of course works. But if you take some simple models, for instance, harmonic oscillators on the sides, this immediately falls. So maybe if I consider these types of models, I can immediately construct such models where I would have a spontaneous symmetry breaking existence at very high temperatures. And instead of just discussing how it could be happening, let me provide immediately use the model that immediately exhibits this property. So for that, I will take a usual Ising model. So this is this square where this Ising model lives. I have variables sigma I and sigma j living at each side of this lattice. But now, additionally, I will add the following bosonic variable Nij that lives on the edges of this lattice. And this Nij will control me interaction strength between my two spins, sigma I and sigma j. So like this way. Nij is positive integer number. At first glance, this model is quite complicated, and I need to take out to understand what's happening here. But actually, for this model, I can immediately notice that all of these bosonic variables Nij could be immediately integrated out using this identity. So I will just resum all these contributions to be very easily performed. And after that, I will notice that product sigma I, sigma j always takes the same value, either plus or minus 1. And each such function that depends on plus minus 1 can always be put in the same type of form, like this. And hence, my effective Hamiltonian, after integrating out Nij, has the following simple form. So it just gets reduced to the original Ising model without Nij, but now the temperature that exists here is different here. It's some original function of original temperature T, and some of this interaction happens A and B. But the very fascinating property about this function is that it's bounded from above. That it satisfies the following bound. So this function has some saturating point when T goes to infinity. And hence, I can declare immediately that by fine-tuning these parameters A and B, you see this function is very simple. I can always find some parameter such that this will be always less than some parameter T. I will make this effective temperature always the critical temperature of this whole lattice model T. And hence, my spin variable sigma I, sigma j will not fill this real temperature T, they will fill only this effective temperature T effective that less than critical temperature. And because of this property, that sigma I, sigma j, they only fill this effective temperature, they will always be in the ordered state. They will cannot go to the disordered state because of they do not fill this temperature. And this always is bounded from above.
And N is has the same sign always?
Yeah, N is integer numbers going from positive 0 plus infinity, yes. Otherwise, it would be unbounded. Bounded. Yes, but you can put here any function.
Why doesn't the limiting effective temperature just mean that the canonical ensemble is breaking down? That, for instance, is what happens in the Hagedorn transition.
But I don't think it's breaking down here. It's just infinite, but it's fine, it's good. I misunderstood your question.
Emo, can you expand your question maybe more?
You need an infinite lattice for that to be the case. You're taking a finite lattice.
No, it's infinite lattice.
Infinite lattice.
It's infinite lattice.
Oh, so it's the, I see, it's the, wait a minute.
I think it should be. There's no issue with that.
What is the question?
So the question is, it looks like there's some kind of limiting effective temperature, no matter how large the underlying temperature is.
Yes.
So
but for this sublattice for sigma I, sigma j, that's all.
all right, let me
So
think.
this sum will converge it, converges very fastly. So
maybe a different way. Maybe well, I don't quite understand the question. Maybe what he's wondering is there an interpretation to the effective temperature?
Yeah, I think that's what I'm asking.
I think it's more or less like a trick, to be honest, here. Like, for instance, you can put sigma and sigma j at infinities there and there, right? And after that, you just write a down partition function. At one step, you will just integrate out immediately n. You will reduce to the Ising model, and after that, use the usual solution of the Ising model given by Ensager. That's all. And after that, you will just notice that effective temperatures that being in this description is always less than critical temperature. So there is no issues with existence of keep state or not existence. It always exists here.
Okay.
Okay. So let me give me interpretation how it's connected to the this Pomeranchuk effect to Rochelle solved. So here we see that sigma I sigma j actually effective chemical potentials for Nij, and where they are in the ordered state. Sorry, I wanted to fix the typo, but I think I created two additional typos. Here should be minus sign, and here should be minus sign. So sigma I sigma j. When they're in the ordered state, sigma I sigma j is equal to 1, and this creates a small, I'm really sorry, the mistake here, when I rewrote it. So it will create a small effective chemical potential for this Nij, and hence when they're in the ordered state, Nij fluctuates much more wildly than when they're in the ordered state. And hence it coincides exactly with this idea for Pomeranchuk and Rochelle salt, where ordered state allows you to fluctuate more for the other substate here. So it nicely fits into this pictures that I provided you before. So now here the order is driven entropically rather than by energetic reasons. Okay, but now you might complain that this model is very complicated. I will not be able to realize it in real life because of now I have to introduce some sort of stage couplings that controlled by these bosonic variables Nij. And so we try to find some much more simple models where the same type of behavior could be exhibited here. So you can see here just like a proof of concepts that we actually can immediately construct such states, such models. So we try to find some models where could be realized on the experiment. And for that, I need my own AI model. Just stands for arithmetic Ising model. Okay. So some of my collaborators doesn't like, so it's called IIM model. So it's model. So it's it. And we didn't know that we just wrote arithmetic Ising, and after that we realized before submission that this becomes AI model. Okay, so let's take the following model, just the lattice gas model that was studied by Lee and Young. This is an ferromagnetic Ising model in disguise. It has the following Hamiltonian. Here I raise an I to the power of k, but it's just like so I can connect to this model because of here a doesn't play any role. I have set a to be equal to 1, and I will see that this model has a first of all finite dimensional Hilbert space locally. For instance, locally this exists maximally mixed state with this following probability. So it satisfies the Brook theorem. It's local and it has of course factorizable Hilbert space. So it satisfies the Brook theorem that high temperature exists in so-called gaseous state. So we see each black cell corresponds to Ni is equal to 0. Each white cell corresponds to Ni is equal to 1. And you see that they are randomly distributed. But as soon as I cool down the temperature in this model, I will encounter this so-called checkerboard state, like this one. So they will nicely arrange to this checkerboard things. It happens because of at low temperatures, I will try to minimize energy. And to do that, I need to first of all get rid of this term and maximize this term. Okay, here also created, here should be minus and here plus. So after that, you will immediately see that there is only two states that satisfy this condition. This checkerboard state and its antipodal, where you replace all white squares with black and all black cells with white squares. And you see immediately that this state breaks symmetry. It breaks shift symmetry here. The original model was respecting this shift symmetry. I can shift by one lattice side and get the same thing. And the gaseous state, you immediately see that the symmetry is respected because of they all well fluctuate. But the checkerboard state, they immediately break with symmetry. Okay, now let us try to play the same games that I played in the last slide. Now I will say that Ni goes not from 0 to 1, it goes from 0 to infinity. And to make my model a little bit better, I will switch the sign of this interaction to plus. And now this A is not some stupid variable, it's a very crucial thing. And for a while, I will consider on the case A more than 1. Let us see what is happening in this model. And since we have lattice model, we can study the Monte Carlo simulations here. And you see that at high temperatures, my system immediately going to this checkerboard state, But now, to distinguish it from the anti-ferromagnetic Ising model, I will draw cells by yellow. It means that here is not 1, 0, 1. It means there could be something of the order 1,000. So you might think it's like a skyscraper moving at this point. And at low temperatures, we have that system exists, so-called gaseous states, that everything is get averaged and equal to each other on average. So we see that in this case, my symmetry gets broken, again, as in the antiferromagnetic Ising model at low temperatures. Here it restored, but at low temperatures. And let me argue why it's happening. So at large temperatures, just in checkerboard state, each yellow cells, the yellow square can fluctuate as much as it wants. Namely, it just feels chemical potential present here. It only feels the presence of this chemical potential mu, and that's why I expect that on average there will be T over mu particles at each white cells. And after that, if I take contribution from this all states, I will get the contribution of partition function for checkerboard state has the following form: T to the power of L squared over 2. L squared over 2 is coming because of only half of the cells are occupied. And now, if I see what's happening in the gaseous phase, now the second term starts to play a major role. Namely, we have this condition, and from that it follows that now each site occupied up to this number, T to the power 1 over 2a. And hence, I see the contribution of each site here is roughly speaking T to the power 1 over 2a. And if I take into account that now all of them occupy some number of positions, I will get the total contribution of partition function is T to the power of L squared over 2a. So here L squared over 2 coming just from how them occupied. Here L squared is coming because all of them occupied. But now we have this factor 1 over 2a. And we see that if a more than 1, the contribution of the checkerboard phase to the partition function dominates over contribution coming from the gas phase for large temperatures, and hence I will expect that this thing will win at the large temperatures. Yeah. So this model is nice, but still looks a little bit complicated because of it requires this polynomial interaction between these two parts. So maybe we can simplify it a little bit. And for that, we came up with so-called simple model of entropic order that we studied much more in details. And the interesting property in this case that now we have a limiting ratio that we must require that mu over mu must be bigger than 1/2. So for that to go to a solid phase at high temperatures like this one, roughly speaking, coming from the previous estimations, but you must do it much more carefully. You can show actually study this model using so-called large K species limit, where you say now at each point here lives not one species of particles but K of them, and reduce the following potential. After that, this model has exact solution with the large K limit, and it confirms qualitatively the same picture. Now you can ask me also what happened with Dobrushin theorem here. I forgot to tell you that actually before first Dobrushin theorem, there was Dobrushin lemma, who said that how to check whether T is contractible or not. And if you apply this lemma here, you'll find out that the Dobrushin theorem tells you that now gaseous phase must exist not at large temperatures, it must exist at low temperatures, below here. I'm speaking at 1/3 here. That. And this model could be generalized, for instance, to the quantum case, where again is a large K limit, we managed to show that despite of quantum fluctuation, it's still the symmetry at large temperatures, at large enough temperatures. Okay. And finally, the last but not least, let me explain to you what's happening in the case of quantum field theory. In this case, we should not be afraid of the evolution theorem from the very beginning. Roughly speaking, it happens because of, first of all, we immediately have infinite numbers of degrees of freedom locally because we have infinite oscillators, speaking at each point of space-time. Second of all, even if you start with some lattice model and go to a critical regime where you have this theory, you might encounter that this critical temperature predicted by the Dobrushin theorem is actually going to infinity. And for instance, that's what we expect in the case of the gauge series. But it's a completely different story. I can explain to you if you want later. So let us consider then the following model. We take our favorite large n vector model for this part. So we have operator phi I, who has dimension t minus 2 over 2, sigma that has dimension 2, and we try to befriend it with this interaction 1/2 dv psi squared. And after that, we try to study what happens when I couple these two sheets with the use of this interaction t sigma psi squared. And this interaction is actually marginal for all d is a large n limit because of sigma has dimension 2, psi squared has dimension t minus 2. So they add up to d. So in the large n limit, you might assume that t is actually marginal and can set to any number, but we must be careful. There are one-variant corrections.
So there is no dynamics for sigma, right?
No, it's usual large n vector model. Sigma is Haber's atomic field.
So sigma enter linearly.
Yes, it's just imposing constraints as phi I squared is equal to 0. But after that, you will study the equation of motion for sigma, and you will find out this dynamical field with dimension 2 here. Rough speaking, this comes and you add cortical interaction phi squared squared, integrated out, says that the second piece is irrelevant, and you will get this interaction. Now you couple it to the form t sigma psi squared. And after that, you study, sigma becomes slightly relevant. And after that, t flows to some fixed point. You can write down the equation for flow for that thing and find out that it flows to the following 3 points. Speaking -1, 0, and 1. First one is very boring. T goes to 1. Roughly speaking, actually, here in this notation, t goes to 1/2. Roughly speaking, it decided to join this point field from all the series to become point +1 dimensional or n +1 vector model. So it's not so interesting. We already know that a lot about the system. We can flow to 0. And after that, this guy just stopped talking to this guy. And it's also not so interesting. But the last solution becomes very interesting. It flows to the case t is equal to -1. And now they try to fight with each other. Let's see how it affects my solution of my theory at finite temperature. And for that, first of all, I need to bring into criticality. That I do by fine-tuning other irrelevant parameters in my theory of flat space-time. And after that, I can study this Lagrangian at the finite temperature. And using that in the large limit, my theory becomes almost classical. I will get the following set of equations, like this one. It's coming from the variation of this condensate of psi field and phi field, and from this equation. They come from the variation of sigma. And interestingly enough, there exists a solution of this form. By setting sigma equal to 0, I can pick psi and phi to be some non-zero value. And if t is equal to -1, this thing allows the following solution. When t was positive for 0, such solution did not exist. And by checking which thing has low free energy, I will find out that actually this solution has low free energy for t less than 1. And hence I must declare that psi must get condensed. And it's equal to condensation. But as you might have noticed that here I cheated a little bit. Here d existed between 4 and 3 dimensions. And to go to 3 dimensions, I might be a little bit more careful, because of here I could add additional term is g psi to the g psi to the 6. That actually becomes marginal in 3 dimensions and could destabilize my theory and render it non-unitary. But after that, you do some sort of computations. You find the function for this coupling G. You find out that there exists actually positive G, and concludes that it's also stable and potentially breaks symmetry at finite temperatures. Let me connect it to this again Pomeranian effects that I discussed before. For that, let me try to compute the entropy of the symmetry broken phase and entropy of symmetry preserving state. So for that, I just compute my free energy as a function of the condensate sigma psi at finite temperature T. Could be done again with the use of the large n techniques. So we'll get the contribution coming from the term fluctuations of large change fields here. After that, I also need to take into account Casimir energy of that large change fields and interaction with the content state. And I can completely forget about fluctuation of the field psi. And after that, using standard thermodynamic relations, I can compute the entropy of my state psi is equal to 0 and psi not equal to 0. And I will find out the entropy of disordered state or ordered state is actually higher than the entropy of disordered state. Roughly speaking, what is happening here is that when I set psi to 0, psi non-zero, I can allow to set sigma to 0. When sigma is equal to 0, these massless fields can fluctuate much more violently when they were gapped. And hence, they have much more ability to explore more of the phase space, and hence it leads to the increasement of the entropy. And hence, from that, I must conclude that again, as in the case of Pomeranian effect, and again, like in the effects of the lattice models that I provided before, here order associated not with energy, here order is associated with entropy. That the entropy of ordered state is higher than the entropy of the disordered state. You might think actually that it's a very big small difference here between these entropies, but don't forget that entropy is logarithm of number of states, and hence this difference will be tremendous. It will be like 1,000 more states with psi is not equal to 0, with psi is equal to 0. And hence, if I randomly draw my state some temperature T, most likely I will draw it with non-zero psi. That breaks the seal. Okay. And so last but not least, I will tell you about this model. It exists in 4 dimensions. Dimensions, it's again ON model, but now it's coupled to this field psi that is now charged some to 1. You can play the same trick as in the case of 3 dimensions, but now you should treat this model some sort of EFT that varied up to some large lambda, because of, if you look at the function, you will see that there is Landau pole here. But nonetheless, you will see again that that thing at all ranges of its validity actually breaks the U1 symmetry. Psi gets condensed and A becomes massive, so leading to this superconductivity. So even though theory is not to be complete, the results still applicable up to finite and very high temperatures here. And again, the same time, we can explain the role that the number of states with sigma is equal to 0 are higher than the states with sigma is not equal to 0.
Maybe can I ask? So, do you think this is inevitable that for a thermal order of continuous symmetry, that would be impossible?
No, there is just this model.
You think there is a way?
We actually have other lattice model for that thing that also breaks U1, but it's a little bit more messy. So I would like to present just this model.
I see, but wouldn't you expect? So, I mean, isn't that isn't that inconsistent with or in tension with the fact that effective field theories are spontaneously broken?
But it's in 4 dimensions.
Right, but that they have irrelevant terms. They're non-renormalizable. They're not UV complete. How is it consistent with the fact that the U1 phase should have an effective field theory at Goldstones that itself is not UV complete?
Well, yes, that's what I said. That is valid of some large lambda. That's what you ask.
So I'm asking if so you say you have a lattice model that you're not presenting.
Yes, lattice models that we don't present. Yes.
Right. Then at very high temperature, there's going to be a Goldstone effective field theory, right? For if you're claiming the U1 is spontaneously broken.
Yes, but also we take into account interaction with gauge fields as Goldstones gets eaten.
So it's not a global U1 symmetry that you're talking about.
Yes, it's U1 gauge theory.
I see. Okay,
So
I thought you were talking about
yes, sorry, I should have been more
symmetry.
explicit. Yeah, see, it's coupled to this U1 background gauge field.
Okay, got it. So maybe I'll ask my question again. Do you think it's possible to spontaneously break a global continuous symmetry at high temperature?
I still think it's.
You think it's possible?
It's possible.
Okay, should I say my argument again for why it should be impossible?
No. Let's discuss that.
Okay.
It sounds interesting, but I think I'm a bit tired of saying okay. Also, it's almost the end of my talk, so we can. So it brings to the idea of existence of so-called entropic order. Roughly speaking, it should be just opposed to energetic order, where we have 2 vacuum states and we were not able to tunnel from one state to another state because of thermal fluctuations were suppressed. Here, thermal fluctuations are not suppressed, but the distance that you must travel from one side of one vacuum state to another state is infinite. So in the case of this arithmetic Ising model, we had like a lot of skyscrapers built at each even lattice side. And to go to the other vacuum state, we need to demolish all of the skyscrapers and start building from again. And since the skyscrapers are extremely big, also the temperature, we must expect that demolishing all of these skyscrapers and building the other one will happen with almost zero probability. So most likely we will just stay around one of these vacuum states. So in contrast, so it should be thought as some sort of opposite to the energetic order, where it's thermal fluctuations. So you can just you have like small occupied unoccupied state, but the thermal fluctuations were still fixed and you're not allowed to destroy this order. Okay. So you see that these models can exist, provided you a lot of interesting lattice models that shows that Monte Carlo indicates that it breaks spontaneous symmetry at high temperatures. So maybe at some point it could be expanded, realized the real infrastructure is out. So thank you for your attention. Yes.
So presumably if you truncate the number of
yes, then you will not be able to cheat Dobrushin's theorem. Roughly speaking, what will happen is that this transition temperature will become quite large. So this transition temperature will become of the order K multiplied by some transitional temperature of the original model.
And the K is like set by the...
Yes. So for instance, if you in this model set that sum is going up to some big number n, you will find out that this effective temperature going from 0 to infinity, but up to very, very large temperature in T, it's linear in this number, it will be below this bound.
So I'm still confused by this model.
Okay.
So there's some effective theory which looks like kind of a standardizing model with some effective temperature. So in that effective theory, there's an effective operator, which is the temperature operator. And you're telling me that somehow, in the effective theory, you naively expect that you could arbitrarily dial the effective temperature. You're telling me that no, the microscopics forbids me from realizing some range of temperatures in the effective theory. So why is it that, if I'm an experimentalist and I'm just, there's some mass operator and energy operator in my effective Ising model, and you're telling me I can't dial that, something's forbidding me from dialing that in my effective theory. What is that thing that's forbidding me from, cranking up the temperature in that effective field theory?
Roughly speaking, I think it lies into this NIJ that they will forbid you to that. I can give you just a technical reason right now that we will just get some that will be effective for less than 10. But right now, I just don't know how to explain it better.
Well, maybe Emil's question is sort of about the stability of this effect. Like the initial Hamiltonian looks a little bit tuned, and that you don't also have sigma I, sigma j.
No, you don't need to tune anything.
But I could have had a bare sigma I, sigma j in the initial Hamiltonian, right? And you don't put it. And if I have a bare sigma I, sigma j in the Hamiltonian, then I'll have a bare.
No, I have bare sigma I, sigma j. A sigma I, sigma j.
I see. And somehow, no matter what it is.
Yes. Like you can dial it up such that it will destroy this temperature. But if you're in this phase, that it persists to high temperature, small perturbations will be stable.
I see. And there's no bare coupling that you can add in the sigmas that will enable you in the initial model that will get you an arbitrary temperature. Like if I deform the initial Hamiltonian by higher powers of sigmas or anything like that, can I get the temperature operator back out?
Sigma goes at 5 hours. plus minus one, but
Yes.
even if in the lattice.
You can,
Well, okay, not next to nearest neighbors.
Next to
Yeah, next to nearest neighbors.
Then it's possible. Then you will count some
Then-
sort of competition there that you must take into account.
I see.
Fedor, is there any relation to working peaking effects?
No
Different story.
difference. But maybe related. They also play the same.
I wonder about, the other loophole was to break the tensor product factorization of the Hilbert
Yeah,
phase.
yes, we also.
You have some examples with the kind of finite degrees of
Yes.
freedom. Could you describe them qualitatively?
Let's do it right. Okay, just will take some time. But you just construct gauge theory, just look at it. You will notice that there's some duality. Roughly speaking, in one picture, you will see that it's potentially break symmetry. In the other case, it doesn't. Okay, it's very abstract, but that's
It's a zero form symmetry. You're still talking about a zero.
Huh?
You're still talking about a zero form symmetry.
Yes, zero symmetry, yes.
What about examples where, speaking of higher form symmetry, higher form symmetry usually follows an inverted pattern of restoration and breaking,
Yes.
where it's typically broken at high temperatures in simple models. Can you invert that?
Maybe possibly so invert here.
You have like a confining phase at high
Yeah,
temperatures.
Since we can do it here, but you must play again some sort of game here.
That's interesting. Yeah.
How
Well,
do you
can
gauge
I-
this model?
How does the Brook theorem kind of aligns with it? Because if I could compactify my gauge theory, right? It says that now some sort of like but actually, if you look closely here, that it inverted. But after you study the lattice model, this the Brook instance, you will find out that indeed the confinement will follow this phase. But on this lattice model, up to very high temperatures, it will go back to the confinement phase.
Yeah. Okay. Awesome.
Any other questions? Okay, let's thank Fedor.